Welcome back to the deep dive. Today we are going to try and fix what I imagine is a pretty traumatic memory for a lot of you listening.
Oh, yeah. Which trauma is that exactly? High school gym class.
High school physics, actually. Specifically, that moment when your teacher introduces the theory of relativity for the first time.
Oh, right. The big paradigm shift.
Yeah, because you spend all this time learning about, balls rolling down ramps and springs, and everything just makes sense. F equals ma.
Very intuitive stuff.
Right. And then suddenly they drop this rule on you out of nowhere. The speed of light is constant for everyone, no matter how fast you are moving.
The famous postulate of constant light speed.
Yes, and it is so maddening because it just feels completely counterintuitive. I mean,
Yep.
if I am in a spaceship doing half the speed of light and I shine a flashlight straight ahead, common sense tells me that light should be moving at 1.5 times the speed of light relative to the ground.
Which would be classical Galilean physics.
Exactly. But the teacher just says, well, no, it's just c. It's always c, because Einstein said so.
You basically have to suspend your disbelief. You are asked to accept that the universe just has this universal speed limit sign posted everywhere, and we all just have to obey it because that is the rule. It feels a bit like magic, not mechanics.
Totally. It breaks the rules you just learned.
Yeah.
But I've been going through this stack of research you sent over. Specifically, this one source. It's a paper called Newton and Relativity by Cester, Clemente, and Korf.
Huh.
And they are proposing something that sounds, frankly, almost impossible.
It is definitely a very bold premise.
They are arguing that we actually don't need to start with that confusing rule at all. What if relativity isn't this massive departure from Isaac Newton's work? What if it is actually just a logical extension of it?
Right. They claim that if you read Newton's original work very carefully, you can actually derive E equals MC² and the universal speed limit without ever assuming that relativity exists in the first place.
Which is just wild to think about. Our mission today is to essentially bridge this gap between Newton and Einstein. We're going to see if we can prove the speed limit of the universe using simple conservation laws instead of all that complex space-time geometry.
And if the authors of this paper are right, we are going to find out that Newton was actually laying the groundwork for relativistic physics 300 years before Einstein was even born.
To do that, we have to start at the very beginning, the source code of classical mechanics, Newton's Principia.
Yes, we have to reread Newton. And this is where a huge misconception usually happens.
Right, because my first aha moment in reading this was about Newton's second law. I thought I knew it. It's F equals ma, force equals mass times acceleration. That's the t-shirt equation.
That is what is in almost every introductory textbook. But here is the fascinating thing. If you open the actual Principia and look at the original Latin, that is not what Newton wrote.
Okay, so what did he actually write?
He wrote that force is proportional to the mutation of modus.
Mutation of modus, so mutation of motion.
Exactly. In modern physics terms, he defined force as the rate of change of momentum, not just velocity.
Okay.
Now, momentum, which we represent with the letter P, is mass times velocity. So Newton is actually saying that force causes a change in the combination of mass times velocity.
But wait, if I throw a baseball, the mass is constant. It's whatever a baseball weighs. So if the mass isn't changing, the only thing that can change is the velocity. And a change in velocity is just acceleration. So isn't F equals ma basically the exact same thing?
In 99% of daily life, yes. And that is exactly why we teach it that way to high schoolers. But strictly speaking, mathematically, Newton's real definition is F equals dmv over dt, the time derivative of momentum.
Oh boy, calculus.
Just a little bit. If you remember the product rule from calculus,
Barely.
when you take the derivative of two variables multiplied together, you get two distinct parts. The first part is mass times the change in velocity, which gives you your standard m.
Right, the one we know.
But there is a second part, velocity times the change in mass.
Velocity times change in mass. So you're saying Newton's original formula actually leaves the door open for an object's mass to fluctuate?
It does. Now, Newton himself never actually saw that happen. He was dealing with apples and cannonballs, not subatomic particles moving at near light speed.
Sure.
But his mathematical structure, the way he phrased the law, was totally future-proof. It allows for mass to change with speed. We just ignored that second half of the equation for centuries because we assumed mass was always a fixed property.
That is amazing. It's like finding out your standard desktop computer has had a built-in quantum processor this whole time, but you never ran a program demanding enough to turn it on.
That is a brilliant way to put it. The authors of the source material are basically saying, let's stop ignoring that second term. Let's see what actually happens to classical physics if we admit that mass might not be constant.
Okay, so we have this real version of Newton's law. But to get to relativity, we need to talk about the elephant in the room. E equals mc².
The most famous equation in the world.
Yeah. And usually that equation is treated as the grand finale of relativity. You learn about warping space and time, and then boom, energy and mass are the same thing.
Yeah.
But this paper flips that entirely, right? They argue E equals mc² should be the prerequisite.
Yes. They present a non-relativistic proof of mass-energy equivalence. They are proving that mass is energy using only 19th century classical physics. No Einstein required yet.
This was the part of the reading that really forced me to concentrate. It involves a thought experiment with a box.
Right. This draws on some classic work by Max Born and Fritz Ehrlich. Imagine a perfectly sealed box floating in deep, empty space. There's no gravity, no friction.
Just a box in the void.
Inside this box, attached to the left wall, is a device that can emit a flash of light. A light bulb, basically. And on the right wall, there's an absorber that will catch that light.
Got it. Bulb on the left, wall on the right.
So the bulb emits a quick pulse of light toward the right. Now, thanks to James Clerk Maxwell's work in the 1800s, we already knew classically that light exerts a physical pressure. It carries momentum.
Radiation pressure.
Exactly. So when that bulb shoots light to the right, what happens to the box?
It's like a tiny gun going off inside. The docks must recoil to the left to conserve momentum.
Perfect. The physical box drifts slightly to the left while the light pulse travels to the right. Then the light hits the right wall and is absorbed. That impact transfers the momentum back to the physical box, effectively stopping it.
So the end result is that the entire box is permanently shifted a tiny bit to the left.
But here is the classical physics problem. Newton's laws state that the center of mass of a completely closed system cannot move unless some external force acts on it. And there were no external forces here.
Wait, but the box definitely moved left. You just said it did.
The physical container moved left. So for the mathematical center of mass of the whole system to stay in the exact same spot, something else inside that system had to move to the right to counterbalance the box.
And the only thing that moved right was the light.
Exactly. Therefore, for the classical equations to balance, that pulse of light must have carried actual mass from the left side to the right side.
Wow. So mass isn't just physical stuff. Sending light across a room means you are literally moving mass across a room.
Yes. Energy has inertia. And if you sit down and do the basic algebra for this thought experiment, comparing the distance the box moved to the distance the light traveled, you find that the mass transferred is exactly equal to the energy divided by the speed of light squared.
Which is m equals E/c².
And if you just multiply both sides by c².
You get E equals mc². That is brilliant.
And we didn't use a single piece of modern relativity to do it, just Newton's conservation of momentum and Maxwell's radiation pressure.
It completely demystifies the equation for me. It shows that the inertia of energy is just a fundamental classical concept. So now we have these two core ideas. The real Newton's law that allows for changing mass, and the classical proof that energy has mass.
And this is where the source builds what we can call the bridge to relativity. We just need to connect those two dots.
Let's walk through that bridge. Let's say I am pushing a heavy cart down a track. I'm applying a continuous force.
Okay. You are doing work on the cart. You are pumping energy into it. In the simplified high school physics view, 100% of that energy goes directly into increasing the cart's velocity.
Right, it just goes faster and faster.
But we just established mathematically that energy has mass. So as you are pumping kinetic energy into this cart, you are technically also pumping mass into it.
So the cart is literally getting heavier the harder I push it.
In terms of its inertia, yes. Now at normal human walking speeds, the amount of mass you are adding is so incredibly tiny, it is basically unmeasurable. But what happens if you keep pushing this cart until it is going at 50% the speed of light?
I would be adding a massive amount of kinetic energy.
Which means you are adding a massive amount of mass. The faster the cart goes, the more massive it becomes. And the more massive it becomes, the harder it is to accelerate it any further.
Oh, I see. It's a feedback loop.
A huge feedback loop. And if you take Newton's real law, F equals the time derivative of momentum, and you substitute in the fact that mass increases with energy, the resulting calculus gives you the famous relativistic mass formula.
That's the one with the square root in the denominator, right? Where mass equals the rest mass divided by the square root of 1 minus v² over c squared.
That is the exact formula, and the source actually uses this really neat geometric way to visualize it called the relativistic EPM triangle.
Right, I remember seeing that. It uses the Pythagorean theorem.
Yes, it creates a right triangle where the sides represent total energy, kinetic energy, and momentum. It shows visually how these quantities scale together without needing to memorize the complex algebra.
It's a great visual. And the crazy thing about that relativistic mass formula is that it explains the universal speed limit without just declaring it as a random rule.
Exactly. Look at the math. As your velocity, v, gets closer and closer to the speed of light, c, that denominator gets closer and closer to 0.
And dividing by 0 is bad news. It means your mass shoots up toward infinity.
Right. It's like you're in a particle accelerator.
Yeah.
As we push a particle close to light speed, it doesn't just keep getting faster, it gets incredibly heavy. So you hit a point where you would need an infinite amount of force to push infinite mass.
Which is impossible.
Yeah.
So the speed limit of the universe is just the natural result of an object becoming too heavy to accelerate anymore. It is not an arbitrary traffic law.
Nature isn't throwing up a stop sign, it's just converting your extra pushing energy into mass instead of speed.
Okay, so that handles E = mc² and the speed limit. But what about the weird way velocities add together? Because that's another thing that always confused people.
The velocity addition problem, yes.
In classical physics, if I am on a train going 100 miles an hour and I throw a baseball forward at 100 miles an hour, someone standing on the ground sees that ball traveling at 200 miles an hour.
Just simple Galilean addition, 100 plus 100.
But if I am in a spaceship going half the speed of light and I turn on a headlight, the light doesn't travel at 1.5 times the speed of light relative to the ground.
No. Experiments show it still just travels at the speed of light.
And normally textbooks just say, well, light is special. Just accept it. But this paper derives a formula for this without assuming light is special.
Right, they do. They derive the velocity addition formula by analyzing a collision between two particles. And they enforce only two rules: conservation of energy and conservation of momentum.
And because energy now includes mass, the math is a lot more complicated.
It is much messier, but the final formula for adding two velocities, v1 and v2, is fascinating. The numerator is just v1 plus v2, exactly like the train and the baseball.
But there is a denominator.
Yes. It is all divided by 1 plus v1 times v2 over c squared.
Let's unpack that denominator for everyone listening. 1 plus v1 times v2 over c squared. If we're talking about normal speeds like the train and the baseball, v1 and v2 are tiny numbers compared to the speed of light squared.
Exactly. So that whole fraction on the right side of the denominator is practically 0. You are left with just dividing by 1.
Which changes nothing.
Yes.
100 plus 100 is still 200.
Right. Classical mechanics works perfectly at low speeds. But if v1 and v2 are huge numbers, like half the speed of light,
then that fraction in the denominator becomes a real significant number.
yeah.
And you end up dividing your total speed by something larger than 1, which shrinks the final answer.
And here is the real twist. Try plugging in the speed of light, c, for one of those velocities. If you are on a ship going 0.5 c and you shoot a laser at 1.0 c.
Okay, so the top is 1.5 c, and the bottom is 1 plus 0.5 c times c over c squared. The c squareds cancel out, so the bottom is 1.5.
And 1.5 c divided by 1.5 is...
It's just c. The math corrects itself. It is literally impossible for this formula to output a number higher than c.
It is a mathematical ceiling. And we didn't build the ceiling because Einstein told us to. The ceiling exists solely to protect the conservation of energy and momentum.
That is the big takeaway here. The constancy of the speed of light is a byproduct. Nature cares about conserving energy above all else. Even basic arithmetic has to bend to keep the energy balanced.
It really reframes everything.
So we have the mass increase, the speed limit, and velocity addition. But we haven't touched on the real sci-fi stuff yet. The concepts that usually blow people's minds on day 1 of relativity class.
You mean length contraction and time dilation?
Yeah. Usually physics classes start with time dilation. They teach that time is relative and everything else flows from that. But you are saying this source puts it at the very end of the line.
It is the absolute final step. It is the cleanup crew of physics.
Explain how that works.
Well, think about the velocity addition we just did. We live in a universe where speeds do not add up simply. 0.5 c plus 0.5 c does not equal 1.0 c. It equals 0.8 c.
Right.
But speed is just a ratio. It is simply distance traveled divided by time taken. So if the velocity part of that equation is capping itself and behaving strangely, then the fundamental definitions of distance and time must be warping in order to keep the math valid.
Ah. So because velocities don't add up linearly, space and time have to bend to make sure the conservation laws still work.
Exactly. The authors detail a thought experiment involving a collision of two electrons. You have one observer at rest and another observer who is moving vertically. For the laws of physics to remain unbroken for both of them, they have to agree that energy was conserved.
And the only way they can agree on the energy.
Is if they disagree on the distance traveled or the time it took. To keep the math perfectly balanced, the moving observer will literally see objects appear shorter in the direction of motion. That is length contraction.
And their clock will run slower. Time
Yeah.
dilation.
The universe is like a very strict accountant. It will distort the fundamental fabric of reality, space, and time just to ensure the energy column sums up perfectly.
I love that. Time dilation isn't some mystical sci-fi aura. It is just the universe cooking the books to protect the laws of thermodynamics. It makes so much more sense when you realize these coordinate shifts, the Lorentz transformations, are derived at the end of the process, not assumed at the beginning.
It shows that special relativity really is just classical Newtonian mechanics pushed to incredibly high speeds.
I want to talk about some practical applications of this before we wrap up, because the source uses these classical foundations to explain some really odd phenomena, like the Doppler effect.
Right. The shifting of light frequencies. We usually think of the Doppler effect with sound, like an ambulance siren getting higher pitched as it drives toward you and lower as it drives away.
And light does the same thing.
It does. But applying relativistic conservation laws to it changes the formula slightly from the classical version. If a star is rushing toward you at near light speed, the frequency of its light shifts toward the blue end of the spectrum. But relativistically, as it approaches the speed limit, that frequency tends toward infinity.
And as it recedes from you, it drops off significantly into a redshift. It is a very clean application of the momentum rules we've been talking about.
There is also a great specific puzzle they include in the paper regarding orthogonal velocities. It is a fantastic brain teaser.
Oh, the galaxy puzzle. Yes, this is a great one. So imagine there's a distant galaxy, and it is moving directly away from Earth at 80% of the speed of light.
0.8 C.
Now, inside that galaxy, there is a star. And relative to its own galaxy, that star is moving perpendicularly, totally sideways, also at 80% the speed of light.
So we have a galaxy receding at 0.8 C and a star moving sideways at 0.8 C.
If you try to solve this with classical high school geometry, you use the Pythagorean theorem. A squared plus b squared equals c squared, so 0.8 squared is 0.64. Add them together, and you get 1.28.
And the square root of 1.28 is about 1.13.
Meaning the total speed of that star relative to Earth would be faster than light, which we know is impossible. So how does the new math handle these sideways vectors?
It is incredibly elegant. Because that galaxy is moving away from us so quickly, the time within that galaxy appears dilated to us on Earth. It looks like it is running in slow motion.
Okay.
Now remember, the star's sideways velocity is just its sideways distance divided by its time. But since its time appears stretched out to us, its sideways velocity appears much slower from our perspective.
So we don't actually see it going sideways at 0.8 c.
Exactly. When you factor in that time dilation and use the relativistic velocity addition, the total vector sum comes out to approximately 0.933 c.
Safely under the speed limit?
Always under the speed limit. The geometry of spacetime naturally compensates to keep that resulting velocity arrow inside the bounds of light speed.
It is completely airtight.
It really is beautifully consistent.
One last thing the source mentioned that I found fascinating was about acceleration. As you get closer to the speed of light, your acceleration actually drops to zero.
Right. Think back to our shopping cart from earlier. Acceleration is simply force divided by mass.
Sure.
But as your velocity gets closer and closer to light speed, your relativistic mass, your inertia, is shooting up toward infinity.
So in that simple division problem, the denominator is getting infinitely huge.
Yes. So no matter how much force you have pushing the ship, you are dividing it by a number approaching infinity, which means your acceleration approaches zero.
You could have the most powerful engine in the universe running at maximum output, consuming insane amounts of energy, and your speedometer just wouldn't budge.
You wouldn't go any faster. You would just keep getting heavier and heavier.
This whole deep dive has been a massive shift in perspective for me. I think so many of us grew up with this vague idea that Newton and Einstein were almost rivals, Or that Einstein came along and proved Newton was wrong about everything.
When the reality presented here is that Einstein essentially saved Newton.
We took just 2 foundational seeds today. Seed 1 was Newton's actual original definition of force, the change in momentum over time, F equals dp over dt.
And seed 2 was the classical pre-relativity realization that radiation pressure means energy has mass.
And from just those 2 classical concepts, we grew the entire forest of special relativity. We got mass increasing with speed, the universal speed limit, velocity addition, and ultimately length contraction and time dilation.
All flowing logically from classical conservation laws.
It really makes you wonder about Newton. He built this incredible mathematical machine based on falling apples and the orbits of planets. He never even dreamed of a particle accelerator. And yet, the underlying code he wrote was robust enough to handle the speed of light.
He essentially built a Formula One race car, but he only ever had the chance to drive it in a school zone. It took Einstein to finally take it to the track and see what it could actually do.
That is a perfect way to summarize it. And it leaves me with a final thought, maybe a provocation for everyone listening to chew on. We spend so much time today looking for brand new physics. We're searching for dark matter. We're trying to understand dark energy. We want to unify gravity and quantum mechanics. And we tend to assume that we need a completely new theory to do it.
We are all waiting around for the next Einstein to rewrite the rules.
But what if we don't need new rules? What if the solution to dark matter, or the accelerating expansion of the universe, is already sitting in a textbook from 1920 or 1850 or even 1687?
What if the equations we already have are completely right, and we are just reading them wrong or ignoring parts of them like we did with Newton's second term?
Exactly. I mean, if E equals MC² was quietly hiding inside Newton's laws for 300 years, just waiting for someone to do the calculus a little differently, what other massive modern mysteries are just hiding in plain sight?
That is definitely the kind of question that keeps physicists up at night.
Well, on that note, thank you all for joining us on this deep dive. Go dust off those old high school physics textbooks. You might just find a Nobel Prize hidden in the footnotes.
Catch you all next time.
Bye, everyone.